Okay, so these lines show the gravitational field strength, so they're the field lines. Another useful quantity is called gravitational potential, and they can be put on these lines here. These lines are called equipotentials, and the numbers here are the gravitational potential. As you can see, in the case of around the Earth, is measured in megajoules per kilogram. So what is gravitational potential? So it's given the symbol V, and a gravitational potential at a point is the work done per unit mass to move a small object from infinity to that point. Okay, we'll look at what this means in a second. So the equation for this would be work done per unit mass. So it's going to be work done, which is just another way of saying energy in joules. Mass is going to be in kilogram. So therefore, the gravitational potential is going to be joules per kilogram. But in the case of planets and so on, we'll use megajoules per kilogram or even gigajoules per kilogram. Okay, to understand what gravitational potential actually means, you need to think about this point infinity, which is a very distant point, or basically it's just somewhere that's so far away that it's outside the gravitational field, or we can treat it as being outside the gravitational field. And we need to consider a unit mass at this point. So basically think about 1 kilogram box like this. Now at infinitely far away, we define the gravitational potential as 0. And we could have defined it as anything, but we define it as 0 because it'll just be convenient. Okay, so gravitational potential will be the work that you need to do in almost pushing this object, if you think about it that way, to bring this unit mass to a point in the field. So imagine we move it to this point here. So that's minus 40 megajoules per kilogram. Okay, so a gravitational potential of minus 40 megajoules would be the work that need to be done to move 1 kilogram from infinity to that point. Let's say I wanted to move it closer, then in that case, the work done would be minus 50 megajoules per kilogram to move from infinity to that point. Explain why gravitational potential around a planet is negative. First of all, we're going to start off with the definition of gravitational potential because it's the work done per unit mass to move a small object from infinity to that point. And we said at infinity, we're going to define the gravitational potential as 0. That's the definition. So a very large distance, there's this unit mass there. And if we want to move it, let's say to the 40 megajoules per kilogram potential, then in that case, what would be the work that needs to be done? The truth is, you wouldn't have to actually do any work because it's an attractive force. So actually, it'll just pull on its own. In that case, it wouldn't be that I need to do work to move it to that point. Instead, actually, energy will be released. So the key understanding here is that weight is actually an attractive force, and I wouldn't have to do any work. Instead, energy would be released. So actually, gravitational potential energy would decrease as it turned with, for example, kinetic energy. In this example, we're asked to calculate the change in gravitational potential energy when a distant object moves to point P, that's marked on this diagram here on the right-hand side of the Earth there. The mass of the object is 200 kilograms. Now, it's tempting to use this equation that we used in year 12 for mgh like this. But remember the G, the gravitational field strength, is going to be changing. We're not in a uniform field, so we can't use this. So to understand what's going on, we need to think about a very large distant point here. So this is what the question means by a distant object. It's so far away, it's basically outside the gravitational field where the potential is 0. And we want to move it to point P. And at point P, you can see from the potential, it's minus 40 megajoules per kilogram. Okay, so that is the change in potential. So we're going from 0 to minus 40. So the change is minus 40. Okay, so it's decreasing by minus 40 megajoules per kilogram. But we're not moving 1 kilogram. We're moving 200 kilograms. So this is megajoules per kilogram. So we're going to have to multiply by 200. Okay, that gives us a gravitational potential energy, which is minus 8,000 megajoules of energy will be actually released. So because we defined as work done, you can think of it as negative work done. In this example, a satellite needs to be moved from A to B along the path shown in the diagram there. So you can see the curvy path there. The mass of the satellite is 1,200 kilograms. Assuming the speed of the satellite at A and B is the same, calculate the energy transfer. Okay, so we're going from the minus 40 megajoules per kilogram to minus 30. So the gravitational potential has increased by plus 10 megajoules per kilogram. But we're not moving 1 kilogram, we're moving 1,200 kilograms. So multiply this by the mass, and that gives you the gravitational potential energy change. The gravitational potential energy has increased because, of course, we're moving it to a greater height from the surface of the planet there. This is actually work done. That's why it's positive here, because we have to push a object away from the planet in order to get it there. So we have to actually do some work. Calculate the work done against gravity to move a 900 kilogram space probe from X to Y. You can see there's a curved path along that minus 30 megajoules per kilogram equipotential. The distance between X and Y is 8 times 10⁸ meters. Explain how you arrived at your answer. Okay, the actual answer here is 0 joules. Okay, why? Well, the simple answer here is because there's no change in potential. You're still at the minus 30 megajoules per kilogram potential, so no work has been done to move between those 2 points. So it doesn't matter actually which path you take. You can take a curved path. If the change in potential is 0, then there will be no work done against the force of gravity to do that movement. Okay, another explanation for why it's 0 joules is to do with the definition of work done. If you remember, work done is a force times the distance moved parallel to the force, and is moving along this line x here. So you can show different points where I've given delta x for the tiny change in distance along the point here. All those points I've drawn on the diagram here, the force is actually at 90 degrees because it's acting toward the center of the Earth there. So the force at each point is 90 degrees. So therefore, there will be no work done because work done is defined as force times distance moved parallel to force. This object never moves parallel to force if it's going from x to y along that path. So that's why the work done is 0. In this final example, the gravitational potential on the surface of the Earth is minus 62.5 megajoules per kilogram. That's on the surface there. An object is fired vertically into the air. Calculate the escape velocity of the object. Okay, so if we wanted to escape the field completely, we basically need to send this object all the way to infinity. Okay, so far away that the gravitational potential is 0. Okay, so we need to think about what is the kinetic energy required in order for it to go up and never come back. Okay, so we can use half mv squared here. So if we're sending it from the surface where it's 62.5 megajoules per kilogram all the way to v equals 0 at infinity, then the change is 62.5 megajoules per kilogram. It's going to have to gain that much gravitational potential. Okay, and the mass that we're moving, well, actually, I don't have the mass of this object. So that's what I'll do is I'll multiply by m here. Okay, so I don't know what that is. And I'm going to make that equal to that's the gravitational potential energy is going to have to gain, and I'm supplying that through kinetic energy. I'm going to fire at very high speed, so I'm going to make that equal to half mv squared. And as you can see now, the m's actually cancel out. So actually, it doesn't matter what the mass of the object is. Obviously, we're assuming a lot of assumptions like there's no we're ignoring air resistance and so on. Okay, so if we rearrange this, we bring the 2 to the other side and then square root it to get the escape velocity, we get 11,180 meters per second, or in other words, 11.2 kilometers per second.